Hey everybody, in this lesson we're going to cover the ideal gas law. An ideal gas is a theoretical gas that obeys all the gas laws we've covered already and the kinetic molecular theory, no exceptions. You can read your textbook for the meaning of theoretical gas, but let's just say for now that there's not one gas that's ideal, but for most problems in science, we can do that approximation and say that all gases will follow exactly the four gas laws. In reality, they don't exactly follow them, but in most cases, yes, for most problems anyways. And just remember, the ideal gas law combines the four gas laws, which were Charles, Boyle's, Gay-Lussac, and Avogadro's law. The four laws have different formulas, but once we combine all of them, they can be expressed as only one formula. So the equation we're going to use for the ideal gas law is PV equals nRT. Pressure multiplied by volume equals the number of moles multiplied by the gas constant R multiplied by the temperature. So P is your pressure, always in kilopascals. V is your volume in liters. N is the quantity of gas, which must be in moles. R is the gas constant, and the unit for this one will be kilopascals multiplied by liters divided by moles multiplied by Kelvin. You have to keep the whole unit every time. And T is the temperature of the gas, always in Kelvin. So R will be 8.31, that's the constant. So the gas constant is 8.31 kilopascal liter divided by mole Kelvin. Example 1. When inflated at their maximum capacity, human lungs contain approximately 4.09 liters of air at 37 degrees Celsius. How many moles of air do lungs contain if the air pressure is 100 kilopascals? So in this problem, we are looking for the number of moles contained in those lungs. And we know the following variables. The volume is about 4 liters. The temperature, when turned into Kelvin, don't forget this one, is 310 Kelvin. And the pressure is 100 kilopascals. Now, N is what we're looking for, the number of moles. So we're going to use PV equals nRT, our ideal gas law, to solve this one because P is known, V, R is a constant, 8.31, the temperature is also given. We just need to find N. So let's isolate that variable. N will be equal to P times V divided by R times T. And once you've done that, you can plug in your values. 100 times 4.09 divided by 8.31. And here, you got to keep all those units. But those are just units. Don't plug in more numbers in there. We already have pressure. We already have volume in there. Okay, those are just units, but they have to be written and multiplied by 310 Kelvin. So the final answer, the number of moles of gas inside our lungs would be 0.159 moles. So here's a nice example of how to use the ideal gas law. Another important topic in the ideal gas law is the molar mass of a gas, because you will have to transform grams of gases into moles or vice versa. So the molar mass, capital M, of a gas can be determined like other substances. It doesn't matter that it's a gas, it doesn't make it any different. By dividing the mass M of the gas by its number of moles N, following this formula, which I know you've seen before. Following this equation, it's also possible to find the number of moles of a gas by dividing its mass by its molar mass. So we're going to use both equations sometimes when working with the ideal gas law. And the ideal gas law can be used to find the molar mass by replacing the value of N in the equation. So remember, that's our classic ideal gas law, PV equals N times R times T. Now, what if we took this N and replaced it by the value of M over capital M, so the mass of the substance divided by the molar mass of that substance? Then our ideal gas law would be turned into capital M, which would be for molar mass, equals the mass in grams times the gas constant, temperature, divided by PV. And here, M can be in grams or kilograms, and that will determine the final unit for your molar mass. So be careful if you plug in kilograms in there. Your molar mass is in kilograms per mole, not grams per mole. Now, most of the time, we're going to keep grams per moles only. Example 2. What is the molar mass of a sample of an unknown gas if at temperature of 0 degrees Celsius and under pressure of 102 kilopascals, a volume of 2.3 liters of the gas weighs 4.23 grams? So in this problem, we need to find the molar mass, and we don't know what the gas is. So I can't just look it up. I have to calculate the molar mass. So the variables known are volume, temperature, changed in Kelvin, the pressure, the mass, and we need to find the molar mass. So we can directly use our new version of the ideal gas law. But just so you know, if you have a hard time remembering this, you can always do your problem in 2 steps. First would be to use your classic ideal gas law, and step 2 would be to find the number of moles. It's just done in 2 steps, a bit longer, but it works as well. So once you have that, we can plug in all of our values with the units as always, and the final molar mass of that substance would be 40.9 grams per mole. And the last thing to add, we need to talk about the molar volume of a gas. What's that molar volume? Well, we have to know that at the same temperature and pressure, so if we don't change that, different gases have equal volumes. So for the same number of moles, of course. So that means whatever gas you have, if you have the same number of moles, they will take up the same volume. So the molar volume is defined like that. It's the volume occupied by 1 mole of gas for any gas under fixed conditions. So molar volume is the volume of only 1 mole of any gas. So at STP, standard temperature and pressure, 1 mole of any gas will have a volume of 22.4 liters, while at SATP, 1 mole of any gas would have a volume of 24.5 liters. And to help explain the molar volume of a gas, because it doesn't sound right that different gases would have the same volume if we have the same quantity of them, because we know that gases have different masses. For example, helium is only about 4 grams per mole, while dinitrogen is 28 and dioxygen is about 32 grams. But that's what we observe if we place them in the same, they're placed in those tanks here. Now we're going to see that 1 mole of oxygen will occupy 22.4 liters, and 1 mole of nitrogen, 22.4 liters, and also, even if it's really small, 1 mole of helium will take up 22.4 liters. So no matter which gas you have, 1 mole of a gas is always equal to 22.4 liters of that gas. And finally, for example 3, how many moles of gas is there in a container holding 73.2 liters of methane, CH4, at STP? So we don't need to write all the variables because we know we're at STP, so that's going to let us write those variables. The volume is given, 73.2. The temperature at STP, that's 0 Celsius, which is 273 Kelvin. The pressure is 101.3, and now we know also this much, that if we had only 1 mole of that gas, the volume would be 22.4. So right now, and again, that's only true at STP. So if we had 1 mole, that would be the volume, but we don't have this much. We have way more. We have 73.2 liters. So we know we have more than 1 mole, but we need to find out how many moles exactly does that represent. So we can just use cross product for this one. If we have 2 fractions, I know that 1 mole is always 22.4 liters, then X moles, and how many moles will be 73.2 liters. So to find my N, I'm going to do 1 mole times 73.2 divided by 22.4. So the number of moles of that gas sample would be 3.27 moles. Like we had predicted, since the volume was greater, at STP, it had to be more than 1 mole.